I hope, in its basic features is known. The reason why neutrino oscillates is very clear. If they have mass, we know they have, so if now is the delta, they have mass, there is no reason why flavor against states and mass against states are the same. And so exactly as it happens with the quarks, the two bases are rotated, there is a matrix that connects the flavor eigenstates with the mass eigenstates. This means that you can have transformation because, of course, the mass eigenstates are the propagation eigenstates. So when you have an emission of a neutrino flavor, because this is the key point, standard model couples flavor eigenstates to the W. So when you emit a neutrino in a weak decay process, you emit a neutrino that is in a flavor eigenstate. The three different mass states propagate with different speed, essentially, in a semi-classical language, and so the phase between these states change over the distance between the detector and the emission, which means that you have the probability to observe one flavor that is a function of the distance of the energy, and the probability is shown there in its very general form. The probability that an alpha type is observed as a beta type at a distance L when the energy is monochromatic is E. The elements U, alpha, I, and such is a 3 times 3 matrix that is exactly, in the case of the quark sector, is complex because there are phases. But there is a difference that now we will see. I hope we will see. Yes, at some point we will see that the phases in the neutrino sector are richer than the quark sector for a reason that I will tell you in a moment. Oh, I already said it discussing the neutrino stuff. Did I speak about Majorana phases?
Yeah, but...
Okay, I will go, anyway I will show you where it comes. In the case of two flavors, there is this very well-known formula that is written everywhere, which is fine to give the idea, but remember that the era of two neutrino flavor is over. Okay? At the beginning of oscillation physics, two neutrino analyses were quite common, because it is true that in many experiments, almost all, there is one oscillation type that dominates, so you can ignore the other one. But this is over, in the sense that this generation of experiments that will happen in the next 10 years, which are the ones that you care, because the ones that have already gone are gone. The forthcoming neutrino generation experiment will not allow the two neutrino analysis. They are all so precise that the full three neutrino analysis is always necessary. Okay? So this formula is there for the purpose of explaining why we are talking about oscillations. The only part that is relevant is this one, because this is still the rule of thumb to understand when an oscillation component matters or not. Okay? So we should remember that the number and those units, the delta n square we know. It's of the order of 10 to the minus 3 for one component and a few 10 to the minus 5 for the other one. So this is the scale of the delta n square that you can have. This is 10 to the minus 5, which means that if this is 10 to the minus 5, you need the 10 to the 5 here. So you need 100 kilometers at 1 MeV. If it is 10 to the minus 3, you need 1 kilometer at 1 MeV. We will see that these distances are important. When you do an oscillation experiment, there are broadly two classes of experiments, which are both useful. So it's not a matter of discussing which is the best one. There is no best one. They give different information usually, and they pose different experimental problems. So they are both useful. One is so-called disappearance experiment, and the other one is so-called appearance. In the appearance experiment, you prepare a beam of known flavor, or you use a natural beam of known flavor. Prepare means includes using natural beams. And search for another flavor in the detector. So you must be sure that the beam is pure in some flavor, or at least as a known contamination, because of course when you prepare artificial beams, they are never fully pure unless physics helps you. There are examples of pure beams, but sometimes they are not pure. And you search for another flavor. An example is with an accelerator, you can make a quasi-pure muon-neutrino beam, and you can either search for electron or tau neutrinos, and both searches have been done. Electron neutrino search is relatively easy. Tau neutrino search is very challenging. Either you use atmospheric neutrinos, in which the composition is known but not very precisely. For example, there are limitations to these techniques, because if you want to study solar neutrinos, it is true that they are pure electron neutrinos, but they are below threshold for the production of the other two. So you cannot search for muon neutrinos or tau neutrinos with solar neutrinos. So that's why I said that both techniques are important. You cannot use appearance all the time. Depends on the energy and other characteristics. So when you cannot use appearance, you use disappearance. You prepare a beam with no intensity. That's the main difference. If you search for appearance, you don't need to be very clever in determining the initial flux, because what you really care is to search for the ratio between the appeared flavor and the non-appear and the original flavor. So you measure in the detector, for example, if you make muon neutrino beam and you search for μe, you count in your detector the number of mu, you count the number of μe, you make the ratio, and you are not depending on the intensity of the neutrino beam because it cancels out. In the disappearance, it's not true, because in the disappearance, you make a beam and then you compare the expected rate with the measured rate. But in order to have an expected rate, you must know the beam intensity. So appearance experiments do not depend strongly on the beam intensity. I don't claim that they do not depend at all, but they depend at second order. Disappearing experiments depend at first order with the neutrino beams intensity, and this is not an easy task. Measurement of neutrino beam intensity is and absolutely non-trivial tasks for reasons that we will see a little bit at least. It's not the best measurement of neutrino beam intensity you can do now. It's 3–4%, no better than that. And you need a substantial effort to measure 3–4%. The main reason is that the neutrino nucleus cross-section cannot be computed very precisely, and it's not easy to measure to better than a few percent. That is not the only reason, but it's the main reason. A note on sterile neutrinos: of course, if you search for additional neutrinos that do not interact with the director, the disappearance technique is the only possible one. But that's why I said that the disappearance is still very important, because it allows you to search for something that you don't know. The appearance requires you to model. I mean, you have to search for something that it appears in the detector, so it's something that you look for. Disappearance has the advantage that you don't need to make any model about the reason why you lost the neutrinos. You simply observe that you lost the neutrinos. Why you lost? It's a different question.
I don't understood the basics of the disappearance detector. I know.
The disappearance?
The disappearance.
So you have a neutrino beam.
Yeah.
You measure the intensity of the neutrino beam, so you know how many neutrinos are produced per second. You put the detector and you count the events. And you compare
whatever flavors. Or
no, for a specific flavor.
For a specific flavor.
For a specific flavor. When you do a beam with a specific flavor, and you look for neutrinos of the same specific flavor. The same. Yes. So, last slide for today, so that next time we start with the status of current knowledge. This is the historical discovery of neutrino oscillations made, announced at the Neutrino Conference in 1998 by the Super Kamiokande experiment, which observed a dependence on the angular distribution of mu1 neutrinos and as a function of the distance between the detector and the atmosphere. If you think a little bit about the geometry, you understand that even if the detector is on the surface of the Earth, due to the fact that cosmic rays are completely isotropic and the Earth is a sphere, you expect the same number of neutrinos from any direction. This is an obvious geometrical fact, because if you are here and you make an angle, and this is the atmosphere, it is true that you are closer to this atmosphere, but this is much bigger and it compensates exactly. Okay? So the number of events you obtain from here is the same number of events you obtain from here, because the 1 over r square effect is multiplied by r squared. So in absence of neutrino oscillations, you expect the mu1 induced by neutrinos reaching the detector to be absolutely the same for all directions. So you expect a purely isotropic flux. And the flux is not isotropic at all. You can see that this is the angle, cos theta is the angle between the verticals. So 1 is vertical, minus 1 is floor. And as you can see, super K observed a neat theta dependence of the muon neutrino flux, which they interpret as oscillations of muon neutrinos to some other component. So this Zenit angle dependence was the first very convincing evidence for neutrino oscillations. In 98. Okay?